try this again. Okay. Wouldn't let me select the laser pointer before it started the recording. Um, okay, so let's move on. We talked a little bit about the basics for hypothesis testing. So let's now get into some of the details. Let's talk about hypothesis testing for population means when you know the population standard deviation. Um, we're going to use a rejection region to draw a conclusion. This would be kind of nice. The use the where something falls on a distribution as our criteria for rejection, and then we'll use the p-value to draw a conclusion. This is just the probability value that's associated with a region on the on the on the normal distribution. Um, so quick review from the last section. General steps in a hypothesis test are to state the null and alternative hypotheses, determine which distribution is appropriate to use, and what the test statistic is, and what level of significance is desired. Gather the data and calculate the necessary sample statistics, and then draw a conclusion and interpret the data. Um, as I mentioned last time, choosing the distribution is we're using the exact same criteria that we used to determine the correct distribution for confidence intervals. You use the same critical values. Um, again, we're going to start with knowing the population standard deviation. It's kind of a simple test, or sorry, not simple test, a simple instance. Um, if the population standard deviation is known, then our z value is given by this equation. We've got the population mean minus, sorry, I misspoke, getting ahead of myself. Sample mean minus the population mean divided by the population standard deviation over the square root of the sample size. Um, again, this is the sample standard deviation according to the central limit theorem. So there are the addendum that the central limit theorem does have to apply here. So the sample size has to be at least 30, or the population distribution is approximately normal. We need a simple random sample. Um, so to determine whether or not to draw the conclusions, we need to determine whether or not our test statistic is statistically significant. So the first method we'll look at here is evaluating the z-scores and use rejection regions. Um, rejection regions are determined by the type of hypothesis test we're after and the level of significance. To find the type of test, we need to look at the type of symbol we've got in the alternative hypotheses. So, if our alternative hypothesis is that something is less than a value, then we're looking at a left-tailed test. If something is greater than a value, we're looking at a right-tailed test. If something is not equal to a value, we're looking at a two-tailed test. We can reject the null hypothesis if the test statistic falls within the rejection region. Erase this, because I probably want it. So we reject the null hypothesis if our test statistic z is less than or equal to the critical z for a left-tailed, negative z critical for a left-tailed test, greater than or equal to z critical for a right-tailed test, or if the absolute value of z, remember those straight lines are absolute value, meaning positive z or negative z is greater than or equal to z sub alpha over 2. So what this looks like on a distribution graph, if z falls below this, this being our critical z-score for one tail, if it falls below that, we reject the null hypothesis, or above that, we fail to reject it. For a right-tailed test, greater than, if z is greater than z sub alpha, we're out here on the graph, and it falls into the rejection region here. If we're after a not equal, so it's two tails, if we're either out here or out here, then we can reject the null hypothesis. Usually there are only a few values of alpha that are used. We had them in Chapter 6. There was a table in Chapter 6 that covered that. That table has been recreated as Table 10.1 in Chapter 10. It's on page 609. Let's double check real quick. It is one of those ones that is on the front cover of my book. I do not know. I know it's not on the front cover of the softback. Let me just check. It is also reproduced right below Table B on page 883 of your textbook. Or almost reproduced. The table in 883 does not show the table in 883 only shows the one-tailed test column. It does not have that two-tailed test column, so you'd have to calculate that separately. You may note that these values match up here. These two match up. And you do need to note that for left-tailed tests, you simply use the negative value under this column instead of the positive value. Alright, so let's look at some examples. If the state education department is considering a new initiatives to boost the reading levels of fourth graders, the reading score on their test was, over the last 5 years, averaged 800. The developers of one of the new programs they're looking at claim that it will raise the mean reading level of fourth graders by more than 50 on that test, so that would probably mean a new average of 850. Okay, there's the key points from that page. So they were told that they did a pilot study. Simple random sample of 1,000 fourth graders had a mean reading level of 856. They're assuming, probably based on prior years of testing, that the population standard deviation is 98. They're using a 5% level of significance. Are the findings sufficient? Do the findings support the hypothesis that this new program will improve the mean reading scores by at least 50? Alright, so null and alternative hypotheses. They want to show that they'll raise fourth graders' mean reading level to more than 850, so means greater than 850. So the null hypothesis, or the opposite of that, is that the mean is less than or equal to 850. So we've got these for hypotheses. Which distribution to use? Let's see, our sample size is 1,000. We've got a presumed population standard deviation and 5% level of significance. So that is known. Sample size is at least 30, so we can use normal distribution and the z-test statistic. We're given that alpha is 0.05, so 5% level of significance. All right, gather the data and calculate the necessary statistics. They've done that. Sample size of 1,000. Sample mean of 856. Population standard deviation was given as 98. Test statistic then is calculated with the sample mean minus the presumed population mean, population standard deviation, and sample size. We get about 1.94. Okay, draw a conclusion and interpret the decision. So, our alternative hypothesis contains a greater than, so we're dealing with a right-tailed distribution. According to the table, I want a right. So the table nicely include this calculation for me. I can do that pretty easily on my own. Too, but I get a critical z value of 1.645 from that. So my rejection region is greater than or equal to 1.645. Value we got was 1.94. So we should be able to reject the null hypothesis based on this. So the conclusion is that we can reject the null hypothesis, so the evidence suggests that the education department can be 95% sure of the developer's claim that the reader scores will increase by more than 50 points on average. Okay, that's fairly clear, fairly straightforward, visually fairly easy to understand. It's not, however, what is usually presented. What's usually found in research journals and articles is p-value gets reported. The p-value is the probability of obtaining a sample statistic as extreme or more extreme than what observed in the data, if you assume the null hypothesis is true. It is essentially the probability that is associated with the z statistic you calculate for your data. If you're dealing with a left-tailed test, it's the probability that it's past the critical z value. For a right-tailed test, it's the probability that it's past the critical z value on the right, so either greater than or less than, depending on which one you're looking at. So as we've done already, we can use the technology, calculator, or Excel. We can use the cumulative normal distribution tables. We've done these calculations. We're just putting them in a new context. Okay, so we want the p-value for a hypothesis test with the following hypotheses, which they'll show you there. Let's assume the data was collected and the test statistic for our data is negative 1.34. Our hypotheses are that the mean is greater than or equal to 0.15, and our null hypothesis is that the mean is greater than or equal to 0.15. Alternative hypothesis is that the mean is less than 0.15. I'm not given the significance level, so we cannot draw a conclusion based on this, but we can come up with the probability associated with that z value. So just go ahead and take a minute and do that, and unpause it when you're ready. can look that up in the tables. Negative 1.34 finds that the p-value associated with negative 1.34 is approximately 0.0901. Like so. That's the area under the curve to the left of negative 1.34. Excuse me. We can do this again. We've got a test statistic of 2.78. Our hypothesis, null hypothesis, is that the mean is less than or equal to 0.43. Research hypothesis is that the mean is greater than 0.43. So I can look up 2.78 in the table or use a calculator or Excel and come up with 0.0027. That looks like. So there's a 2.7 z-score of 2.78 there. The area to the right of that is 0.0027. Okay, again, same type of thing. We've got z-score of negative 2.15. Null hypothesis is that the mean is equal to 0.78. Research hypothesis is that the mean is not equal to 0.78, so we're dealing with a two-tailed distribution here. So we need the z-score associated with 2.15. So 2.15, we find that it's 0.0158. So that is the area to the left of Z1, the area to the right of Z2. So remember, since we're looking for a two-tailed thing, we've got the area below negative 2.15 and the area above 2.15. So we'll be taking that and multiplying it by 2 to get 0.0316 is our total probability here. So we've got these two areas. So our p-value associated with those two areas is what we're after. Okay, so again, we can do this with the TI-8384. This is, again, that exact same scenario with the reading scores. I'm not going to go back over that. Hypothesis was as follows there. So this was in. We want probability that mean is greater than or equal to 856. So that is, no, 856 was the sample mean given. So if we input it into our calculator, following those directions, put in that formula, we're dealing with the normal function. There's sample mean we're testing. We're after a right tail, so we just pick a really large number off to the right. The presumed mean, standard deviation, hit enter, and it will spit out our probability. We do eliminate rounding errors, so it's slightly more accurate. We can do the entire test in one fell swoop, including the calculating the z-score. Okay. So that's how we find the p-value. If to use the p-value, it's simple. If the p-value is less than or equal to our significance level, we reject the null hypothesis. If the p-value is greater than our significance level, then we fail to reject the null hypothesis. So if you want your data to to show what you think it should show. The p-value is something that would ideally be as small as possible. So for some certain hypothesis test, we don't know what, we have a p-value of 0.0146. If our level of significance is 0.05, what is the conclusion for this hypothesis test? If we're after a 99% confidence level, again, the confidence level and the significance level together add up to 1. So 99% confidence level gives us a 1% significance level, or alpha equals 0.01. What is the conclusion at a 99% confidence level? Okay, so at alpha equals 0.05, our p-value is less than that, so we can reject the null hypothesis. At 99% confidence level, we have a alpha equals 0.01. Now we are greater than 0.01, so we fail to reject the null hypothesis. Okay, but it's really pretty simple, and you can fail or reject the same data depending on whether on your desired significance level. Okay, so we've got one researcher who claims that the mean age of women in California at the time of their first marriage is greater than 26.5 years. He did a simple random sample of 213 newlywed women in California and found a mean age of 27 years. So assuming the population standard deviation is 2.3 years and using a 95% confidence level, is there sufficient evidence to support this claim? Can he reject the null hypothesis? Alright, so let's state our hypotheses. Research hypothesis is that the mean age is greater than 26.5. Logical opposite is that it is equal or less than 26.5. So we can state them thus. Alright, so which distribution to use? Sample size is 30. Population standard deviation was known, was a simple random sample. So we can use a normal distribution to calculate the z-statistic. We were told to use 95% confidence level, so alpha is 0.05. Alright, they've gathered the data and calculated the necessary sample statistics. Well, not calculated the sample statistics yet, but gathered the data, and they got a sample mean of 27.0. Sample size of 213, population standard deviation of 2.3. So we can calculate this test statistic using our handy dandy formula here. Sample mean minus population mean, or in this case presumed population mean. Sample standard deviation and sample size. And we get a 3.17. Okay. Alright, so we're after greater than only, so we're after a right-tailed test. So looking that up, we're in one-tailed test. Our critical z-value is 1.645. The z-value we've come up with is 3.17. So based on that, we would be rejecting it. We're after p-values, though. So, which when you're not using the table is more convenient because you don't have to stop at the z-value. So we find the probability associated with 3.17, and that comes to 0.0008, which is quite a bit less than our alpha of 0.5, so we can reject the null hypothesis. we can say with 95% confidence that there is sufficient evidence to support the claims. Okay, so we've got a study that shows that the mean number of children for women in Europe is 1.5. There is a global group that's claiming that German women have a different mean fertility rate. So their mean rate is not equal to 1.5. To test the claim, they surveyed a simple random sample of 128 German women and got a mean rate of 1.4. The population standard deviation is assumed to be 0.8. Is there sufficient evidence to support this claim at the 90% confidence level? And for my own sake, I need to remind myself I'm not stopping at the rejection area, I'm going to the p-value. Okay. They need to find the evidence that the mean fertility rate is not equal to 1.5. So mean fertility rate not equal to 1.5. Logical opposite then is that it is equal to 1.5. So null hypothesis is that the mean is 1.5. Research hypothesis is that it's not 1.5. Okay, what distribution do we need to use? And what level of significance? So we were given a 90% confidence level. We've got, what was it, 120 some samples. So our sample size is greater than 30. We know the population mean, so we can use a normal distribution and calculate disease statistic. 90% confidence level, so that should be a 10% significance level. All right. Their data is that the sample mean is 1.4. Population mean we're presuming is 1.5. Population standard deviation is 0.8, and the sample size is 128. So we can calculate the test statistic, sample mean minus population mean over population standard deviation divided by the square root of the sample size. And we get a negative 1.41. Okay, so we're dealing with the not equal to, so this is the two-tailed, so we need the area that is less than negative 1.41 and greater than positive 1.41. Right, so we're after the sum of those areas. We get 0.0793 on each side. Add those up, we get 0.1586. So 0.1586 is greater than our alpha value of 0.1. So we fail to reject the null hypothesis. So at the 90% confidence level, the evidence does not support that German women are differently fertile than other women in Europe. We can also do this with the TI-8384. Steps 1 and 2 will be the same, so we'll just kind of skip past those. Got our statistics there. Let's just zero test, choose stats instead of data, input our stats that we have. As so, input the null mean there is mu sub 0. Input the sample standard deviation, the sample mean, sample size, and looks like you've got the option of telling it which type of test you're after, left, right, or not equal, two-tailed. The output screen here then gives you that probability right there. Does this nicely in one swoop. Gives you the Z statistic as well. Looks like you have the option to draw it instead of calculating it if you want. So we get approximately the same value, not identical, again, due to rounding error. Same value, still greater than alpha, so we still fail to reject. Okay.